All right, good afternoon. Today we're going to wrap up chapter on BJTs. We're going to go through 4 applications and actually five applications. The first four are simply with the BJTs, either as an amplifier or as a switch. And then we're going to look at transistor and diode logic gates. Okay. So again, in the interest of trying to catch up, all my notations and annotations are already there on the class notebook. You have them available at your end. We are simply going to um, go through the explanation. All right, so we stop here. The BJT self-biasing circuit. First application up is the large signal amplifier use of a BJT. And we are using this to amplify the signal that's coming from a diode. The diode is being used as a temperature sensor. The property that we are using is the diode voltage property as a function of temperature. Now, the diode voltage changes as a function of temperature. This change is pretty well documented and studied, and it is very linear. So the diode voltage changes linearly with any change in temperature. An approximate change is about 2 millivolts for every degree C change in temperature. And it's a negative temperature coefficient, meaning as the temperature increases, the diode voltage decreases or drops by 2 millivolts. Okay. Most digital thermometers on the market that you see today are diode sensor based. All right, so let's look at our circuit. We have a standard BJT and we have a diode. The output of a diode is connected and fed into the base of this BJT. Okay. I have divided the circuit as a sensor on the left and an amplifier on the right. In reality, though, all of this would simply be part of the sensor circuitry. Okay. This is, of course, we are looking at the most fundamental level. And so I'm breaking it up as sensor and amplifier on the right. Obviously, this is simply taking the diode electrical voltage and current signal and amplifying it and feeding it into a logic instrumentation circuitry. All right, so we are not discussing that. That's not part of this of our topic. Okay. So this is essentially a design problem or a design example. We want to design a temperature sensor or a thermometer to operate between 0 degrees C and 100 degrees C. Translated into Fahrenheit, how much is this? Anyone? Is it 0 degrees Fahrenheit? 32 Fahrenheit. And 212, boiling point. As a quick summation, if you want to move between Celsius and Fahrenheit, if you have, let's say, 20 degrees C, you double it and add 32. So about 40 plus 32, 72 degrees Fahrenheit. So C times 2 plus 32 gives you F. Those are not your grades, by the way. Anyway, that's just kind of quick conversion. All right, so design parameters, we are converting, so we are applying the BJT to work as a amplifier, meaning we should bias the BJT to operate in the active region. We don't want it going into the cutoff or saturation region. We want it to be in the active region. Otherwise, our diode signal will never be amplified, right? It will simply behave like a constant current source, which is not desirable. So the output of a sensor, whether it's diode based or any other kind of sensor, would be kind of small, either smaller voltage or very small current. So before we apply this sensor output to our instrumentation systems, right, we need a way to convert the electrical signal and translate it into a readable display, right? We want to convert it into like degree Celsius, degree Fahrenheit, which is what we have here on the wall, right? So in order to do that, we use a BJT. So that small signal coming from the diode is now amplified. So if you want to operate between 0 and 100 degrees C, we want to bias the transistor somewhere in the middle of our desired operation. So middle of the active region and middle of the desired operation. So VCE should be set somewhere in the middle around 50 degrees C. So everything that we work on in the circuit is a temperature of 50 degrees C. Okay. At 50 degrees C, VCE is about 6.5 volts. Okay, 6.5 volts. And the diode voltage is approximately 0.8. Technically, what I see here is 0.78. Okay, for convenience sake, let's use 0.8. Makes it easier to calculate. All right. So one of the other things also is that when the diode is on and its current is large, then ID is near constant. It's a steep slope, right? As a diode current as a function of voltage is a very steep slope, right? It exponentially rises. But we can treat it as near constant. And if you want to do that, if you want to hold the diode current at a near constant level, what we can do is we can bias the diode with a resistor and apply a voltage that is far, far greater than the diode voltage. So in this case, the diode voltage is around 0.7, 0.8 volts. And we can bias the diode with a voltage in excess of, like, say, 10 times or more than 10 times, right? So if it's 0.8 volts, we should apply at least 8 volts VCC. No matter what value we choose for our VCC, we should design our system that the BJT VCE output voltage is about half of that VCC. So if VCC is 10 volts, we choose VCEQ as 5 volts. If VCC is 12 volts, then VCEQ is 6 volts. Okay. All right. So if VCC is far, far greater than ID, far, far greater than VD, then ID would remain near constant because it is flowing through this resistor right here, RS, right? Coming from the top, splits into two. IS is equal to ID plus IB. So if I apply KCL, can write IS is equal to IB plus ID. Now, IB is going to be very small or very negligible. And then we can write IS is pretty much equal to ID. So if we keep IS constant, then ID would be almost constant, right? Because that's the entire current that's coming from the top. Okay. To calculate IS, you can simply apply Ohm's law to this resistor right here. RS is connected between VCC and VD. So VCC minus VD over RS gives me IS, right? And then RB is connected between VDD and VBE. Okay, VDD and VBE. Now, for all intents and purposes, VD and VBE would be very, very close, right? Very, very close. But we want to ensure that the current into the base flows into the base and not out of the base, right? We have resistor RB. We want to ensure that the base current is going in and not coming out. And to do that, we need to ensure that diode voltage VD is larger than VBE. And that can be done when you're choosing a specific component for use. So we choose a diode that has a diode voltage of about 0.8 in this case, but should be larger than the VBE at that same given temperature. And the difference should be very, very small. We want VD minus VBE to be about 0.01 volts, 10 millivolts or so, right? They will technically be very close in value, but we want it to be very small. So IB is VD minus VBE divided by RE. VD, of course, is very close in value to VBE. We want IB to be very small. We want to select RS and RB such that IS is far greater than IB. We want to keep IB as small as possible, right? And so we'll choose a value for RS such that IS is far greater than IB. That would mean IS is equal to ID. So if we choose a large enough current, let's say 100 milliamps. So we choose ID as 100 milliamps. From there, we can approximately write VD as, VD is actually 0.78, as I said. For convenience, instead of 0.78, let's, just for this example, not a real life design, obviously, but let's choose it as 0.8. If it's 0.8, we get 12 minus 0.8 divided by 0.1, which is 112 ohms. Okay, so you can choose RS as 112 ohms, 112. Now, real life values for a resistor, we do not have a resistor with 112 ohms. Closest are 100 and 120. Okay, if you choose 120, larger resistor, current is small. If the current is small, then maybe the diode voltage drops. So it's no longer within our tolerance at 50 degrees C. So instead of that, we choose a larger, smaller resistor so that IS is large. So if IS is large, then our diode voltage would be closer to our desired value. So RB and RS are 100 ohms. Now we go to the output side. VCE is 6.5. You apply KVL at the output. When you apply KVL at the output, we have three voltages, ICRC drop and VCE. So VCC minus ICRC minus VCE gives us 0. We know IC is beta times IB. You write the equation for IB. If you assume VD minus VBE is 0.01, we can calculate IB as 100 microamps. 100 microamps. If IB is 100 microamps, we can calculate IC from the given beta value as 17 milliamps. Once we have IC, we can calculate RC from that value. It's 353, not a real life value. In real life, we would use a resistor that would be close in value. Okay, let's take a pause while you think over all of that and let me know if you have any questions. It's not easy to analyze something. Yes. Yes, approximately in the middle. Yes. Technically, there are, so this is a very rudimentary circuit, most basic circuit without accounting for many environmental conditions or factors. One of them is, of course, the transistor beta. This is a 3904 transistor. if you plugged in another transistor of the same model from the same manufacturer, the beta could be different. If the beta is higher, then the collector current would be larger. If the collector current is larger, it could drive the transistor into saturation. And if it drives it into saturation, it's no longer working as an amplifier. Then the system as a whole would no longer work. So there are quite a few factors that we have not taken into account. Okay. But the steps and approach would apply for all kinds of circuits, no matter what the application is. Okay. In this application, we want active mode. We do not want saturation. Okay. Right. Now, the next circuits that we're going to look at, this one was for active region. Next one is going to bias the transistor in saturation and cutoff. All right, so this one's an LED driver. And the next three ones, meaning here for LED driver, the motor driver, and the battery charger. All of them have the device connected to the output of the collector. Okay. And then a small signal at the base is biasing the transistor either in the cutoff and a saturation region or in the active region. Okay. So we saw the application of the transistor in the active region. Now we're going to look at it in the cutoff and saturation region. So in real life, oftentimes you may have come across a system where an event occurs and an LED turns on or a light turns on, right? Perhaps it's a counter counting the number of people entering a building. Perhaps it may be a system where it says, okay, whatever process was under operation is now complete, and the light turns on, or it may turn off, as the case may be. But regardless of what the application is, you may have a sensor circuit or you may have a microcontroller, and the output of that circuit needs to be displayed visually. So you use a visual indicator like a lamp or an LED. Now, the output of the sensors and the microcontrollers are weak in the sense that they are not able to provide the current required to turn that LED on. So in those kind of cases, we use a BJT. The BJT is simply used as a switch. So you have plus 5 volts. And this is connected to a switch. Okay. So we have an LED. We have connecting a power to the LED. It's like a flashlight. You have a manual switch on the flashlight. Simple circuit. You have batteries in there. You have a filament light bulb. You turn the switch on, makes the connection, and lamp turns on. LED flashlights, the same thing. You have a power source, manually flip the switch, power source is connected to the LEDs, it turns on. And that's all we are doing here. This is a digital switch. It's a BJT. And the BJT is cut off. The switch is off. When the BJT is in saturation, we say the switch is on. Okay, digital switch. That's all we're doing. So we want the transistor to supply a constant amount of current going through. So the obvious conclusion is the transistor should operate in the saturation region. We do not want to use it as an amplifier. We want to use it as a constant current source, meaning in the saturation region. So if you want to do that, we can portray the BJT and the LED by large large signal models. If it's operating in the saturation region, the collector emitter voltage VCE is saturated. So VCE sat, which is about 0.2 volts, and the voltage to turn the LED on is about 1.4 volts. So we can model both of them as constant voltage sources. Okay, VLED and VCE sat. Okay. If you apply KVL around this loop, we have one battery, one voltage drop across RC, one voltage drop across the LED, and one voltage drop across the collector emitter terminals VCE. VCE sat is 0.2 volts. VLED is 1.4, so that's 1.6 volts. 5 minus 1.6 gives me 3.4 volts. That is the voltage that is dropped across the collector resistor. Now, IC, the collector current, should be equal to ILED, the current that is required to turn the LED on. It's about 30 milliamps. So from there, we can calculate RC, right? RC drop, RC IC drop. And if we wish the transistor to remain in saturation, the base current must be large. It cannot be small. It must be large. Okay. Again, if it's small, the injected current going into the base, meaning the input is small, then the output is going to stay in the active region. It's not going to go into saturation. So we want the base current to be significantly larger. So we achieve that by applying V on minus V gamma, 5 minus 0.7 divided by 1,000. If we use a larger value of the base resistor, like say 10K or 15K or anything larger, the base current would be small, hence the collector current would be small, hence VCE might not drop. It'll remain in the active region. But if you want to drive it into saturation, so IB is large. In order to keep IB large, we lower the value of RB. So RB is kept at 1 kilo ohm. Once we calculate that, we obtain IB as 4.3 milliamps, quite a large value. With 4.3 milliamps, if you take the ratio of IC to IB, it's going to be less than 7. Typical transistors have beta ranging from like 30, 35, all the way to like 2 or 300, right? So no matter what value of RB we choose, as long as it's small enough to keep it under 10, then the gain IC and IB will always be far less than the beta of the transistor. So you could plug this transistor out and plug in another different transistor in there, and the circuit would still function just fine. Okay. All right. So now, once we have that, one final check is to check the power distribution of the LED, which is still less than 100 milliwatts. So our design is verified. All right, let's take a pause. Let me know if you have any questions. Yes. So the question being asked is how do we know what VC sat is? That's a property of the transistor. When it goes into saturation, VC is typically 0.2 volts or less. So VC sat for pretty much almost all transistors would be about 0.2 volts. Sometimes it could be like 0.3 or so, but 0.2 is the standard accepted value. Other questions? Okay. All right, let's go to the next two applications. One is the battery charger. The one after that is the motor driver. In all these cases, the output is connected at the collector. In the battery charger, the battery is connected in series with the VCC and the collector terminal. So current passes directly through the battery before it gets to the collector. All right, so simple biasing circuit. We have one base resistor, but in this case, the base resistor is broken up into two parts. One is fixed R1, the other one is R2. And R2 is a variable resistor. Value of R2 varies between R2 minimum and R2 maximum, given by the multiplier alpha. If the arrow is positioned to the left, alpha is equal to 1. The full resistor value of R2 is available in that circuit. If alpha is equal to 0, then the entire R2 resistor is bypassed. Right? If the arrow is here, it's completely bypassing that resistance. Okay. All right, so we want to bias the circuit such that the transistor again should operate in a particular region. What region would it be? You see that we want the BJT to function as a constant current source. It functions as a constant current source. It could provide any current between 10 milliamps and 100 milliamps. Okay. Now, here's the thing. This example uses a 9-volt battery, right? So if you want to charge a battery, obviously the power source must be larger than the battery itself, right? We charge our phones and our tablets with a 5-volt charger. Our batteries inside are about 3 or 3.5 volts, like 3.2 or 3.6 volts. Okay. We can also buy batteries off the shelf, like AA, AAA size. You can plug and charge from any USB port. So again, 1.5 volt battery, you're charging from a 5-volt terminal. So if you want to charge a 9-volt battery, our VCC charging supply should be at least, I would say about 15 to 16 volts at least. Okay. But theoretical design. So let's say it's 12 volts, right? If it's 12 volts, what does it mean for VCE? It means VCE is at least 3 volts. If VCE is not 0.2 volts, that means it is not in saturation. In order for the transistor to be saturated, VCE would be 0.2 volts, meaning VCC would just be 9.2 volts, just barely larger than your battery voltage, which is not a practical design. Our circuit would most likely not work at all. So VCC, the supply voltage must be far larger than your battery. So if the battery is 9 volts, the supply should be larger than 9 volts. 12, 13, 14, 15, just to be safe. So even if we choose 12 volts, then your VCC is 3 volts. If VCE is 3 volts, that means the transistor is not in saturation. It is operating in the active region. Cutoff is not a possibility. If it's cut off, then there's nothing going on. The circuit is completely dead, right? So it's not cut off. So it's not saturation, it's not cut off. The only thing left is active mode. The transistor is operating in the active region. All right, if it's operating in the active region, we can write an expression for IB. IB is VCC minus V gamma over RB. Simple again. RB is connected between VCC and V gamma, which is VBE, basically the base emitter voltage. And we develop an expression for IC. Now, designing, in this case, meaning determining the values of the components, the base resistance, right, R1 and R2. So let's first find R1. We'll maximize the current by minimizing R2 all the way down to 0. The way to do that is alpha is equal to 0. The slider is pulled all the way to the right. Alpha is equal to 0. So R2 is equal to 0. Hence, I would obtain maximum current. And the maximum current is 100 milliamps. When R2 is equal to 0, calculate R1 as 11.4 kilo ohms. Okay, 11.4 kilo ohms. And then once we have R1, we can plug it back into the same equation and calculate R2. So when alpha is 1, R2 is R2 max. When it's maximum, IC drops to its minimum, which is 10 milliamps. And we calculate R2 max from this equation, which turned out to be 102.6 kilo ohms. All right, let's take a pause. Let me know if you have any questions. Yes. Alpha is just given as the constant of variability for this resistor right here. So this is a variable resistor. Anytime you have a component with an arrow pointing through it, it indicates variability. So it could be a variable capacitor, variable inductor, or a variable resistor. And the arrow is simply, is just pointing the position of the slider somewhere in the middle. And so the author just uses alpha as an example. Okay. Any other questions? All right. So once we have that, we can find R2 max. When resistance is at maximum, the current would be at a minimum. So we plug in IC as 10 milliamps and calculate R2 max value as 102.6 kilo ohm. Okay, 102.6 kilo ohm. Any other questions before I move on? Okay. Same thing, same circuit, but now we have an additional circuit at the output because we want a very large current flowing through for this application. This application is regarding a DC motor. DC motors require a sizable amount of current. In this case, our DC motor requires current to flow from 110 milliamps to 2000 milliamps, a really large amount of current. Okay, so we're asked to find the values for R1 and R2. So the first resistor alone is not sufficient to drive the DC motor. So we take the output of the first one and feed it back as input to the second one. So IE1 is equal to IB2. Okay, IE1 is equal to IB2. But regardless of what it is, we can see this is the exact same circuit as the previous one. R1 and R2 are in series. And because they are in series, I can write an expression for IB1 and then IC2. from here. Same principle as last time. To obtain maximum current, the resistance must be at a minimum. So R0, so R2 is equal to 0. You can determine R1 as 8.768 kilo ohms. Minimum current occurs when alpha is equal to 1. And R2 max is 152 kilo ohms. What this allows us to do is multiply the gain by the thousands. So this kind of transistor configuration, the beta of the transistors is multiplied because the output of the first transistor is fed as input into the second. So the first one is a beta of 100 and the second one is a beta of 100. The overall beta of that configuration would be 10,000. Okay, so it's amplifying the current to a very large number. All right, about 12 minutes left. Gates and switches. So we saw the application of two diodes to create an AND gate. What kind of gate do you think this is? Been doing your reading? That's good. Truth table for an OR gate. OR gate or logic OR operation is a mathematical addition. And so 0 plus 0 gives us 0, 0 plus 1 gives us 1. So any one of those inputs is high, the output is high. Okay. We can use the ideal diode analysis to use. And I'm just going to analyze one case. That's VO, short circuit, open circuit. That's all it is. If you apply, sorry, not DA. If you apply 0, 0 at both anodes, diode is off. Diode is off, V out is off. V out is 0, connected to ground. But if you apply logic 1, meaning plus 5 volts, then the diode goes on. VO is equal to logic 1, or maybe plus 5 volts. So either one of those diodes turns on, output is 1. So very rudimentally and most fundamental of OR gate. Okay. All right. Lastly, we have the BJT switch. This circuit by itself, the most fundamental of BJT circuits, one BJT can be used as a inverter circuit. I'll explain how and why. V in is 0 or plus 5 volts. Logic low or logic high, right? If you give 0 as the input, what is the base current? Yeah, 0, right? If the base current is 0, what happens to the base emitter junction? Well, if there's no input, it doesn't turn on. Because it doesn't turn on, the only mode the transistor can operate in is cutoff. So it's completely off. And if it's off, VO is connected directly to the output. So V in equal to 0. BJT is cut off. VOS plus 5 volts. Input is 0, output is plus 5 volts. Logic 0, output is logic 1. Inverted or inverter. The opposite happens when V in is equal to 1. Or instead of 1, let me write it at plus 5 volts. BJT turns on. And because it's on and it's large enough, we can say BJT is saturated. If BJT is saturated, then VCE sat, current is maximum, saturated. So VCE sat, or my VO is 0.2 volts. And 0.2 volts is logic low or logic 0. So 0 as input, you get 1 at the output. 1 as the input, you get 0 at the output. And you're operating the BJT transistor as a switch between cutoff and saturation. The most rudimentary and the most fundamental of inverter circuits. And that's how you can implement a gate. Now, obviously, real life gates have to account for a lot of conditions and a lot of variables. Okay, so real life NOT gate or a real life inverter gate is not simply just a single transistor. It has multiple different inputs like clock signal, enable, set, reset, preset, lots of other inputs. Okay, but it is possible to implement a rudimentary gate using diodes and just transistors. So that's another application. Okay, this brings the BJT chapter to an end. We are all caught up now, and from Friday onward, we'll begin FETs and logic gates all the way to the end of the quarter. Okay, yes. Yes. So it's used as a 2-input gate or a 2-input or a 3-input or 4-input gate too. Mm-hmm. It depends on the circuit and depends. So the question being asked is about the example in the reading assignment where the BJT had 2 emitter terminals. And those are for to implement like multiple input AND gates, multiple input gates, period. Multiple any kind of gates. So it just depends on how the circuit is configured. So yeah, it is possible that one of them could be forward bias, the other could be reverse bias. That is absolutely true. It is possible. Yeah. All right. We're going to end class here today and we'll pick up here on Friday for the final chapter.